This final set of 3 lectures is going to look at advanced techniques and technologies associated with diagnostic ultrasound. So these are things which have been developed over the years that extend the capability of ultrasound or improve it. In this lecture, we'll be looking at compound imaging and harmonic imaging. In simple scanning, each point is looked at just once, and we end up with an image that I've sort of sketched below, where we have a fairly coarse speckle pattern. And if we had a cyst, for example, we would only see part of the walls, that part of the walls where the beams are hitting the walls at approximately 90 degrees. So we'll get a very partial display of those tissues. This illustrates what's meant by compound imaging. The machine actually produces a number of images. 9 is a typical number. Every time the beams are steered in a different direction. So there are 9 images, all of them different, because in each case the beam has been steered differently. The result is that every point in this image is going to be seen 9 times from different directions, and therefore, as you'd expect, we get a more comprehensive image. This illustrates the idea that we will have multiple images, each of them different, and they will then be added together to produce the final compound image. Notice that the speckle pattern in each of these is different, and so when they are averaged together to produce the final image, the speckle pattern will be finer and less pronounced. Notice also that the part of the cyst wall that is imaged is going to be different in each image because the beam direction is different. And so when we combine those images together, we get a more complete display of the walls of that cyst. So these are the 2 primary things that compound imaging wins us: finer and less pronounced speckle, and also more complete display of tissue boundaries. Here is an image of a leg. The upper image is a conventional or simple scan, and the lower image is the compound image. You'll notice in the compound image that the speckle is much less obvious, much less distracting, and also there is indeed a sense that the tissue boundaries and the tissue structures are more complete, and it's easier to figure them out. So there is improved clarity in the imaging of tissues, tissue boundaries, and reduction of speckle. Here's another example. This is a popliteal artery. The standard image on the left shows quite a coarse speckle pattern and quite a significant amount of artifact echoes within the vessel. This is probably a combination of reverberation and perhaps some slice thickness artifact as well. In the compound image, in the center of the slide, you can see the speckle pattern is very much smoother. The tissue structures within the surrounding tissues are clearer, and the artifact in the vessel is still visible. It simply has a slightly different appearance. One other thing I'll draw your attention to here is the intimal layer of this vessel, this artery. In the standard image in the top left, it's nice and clear. In the compound image on the right, we see that the image is rather less clear, so the intimal layer is less crisp, less clearly defined. And this is probably a combination of 2 things. First, the beams are coming from many different directions, not just at perpendicular incidence. So we have a beam width effect causing some blurring and thickening. But secondly, when you stop to think for a moment, you realize that the machine has to acquire 9 successive images and then average those together. Naturally, if there's any movement, then there will be blurring. So I think that's probably the primary reason that this image looks less crisp than the simple scan in the top left. This illustrates one other aspect of compound scanning. You've seen this image before. It's a cyst in the breast, which doesn't look like a cyst because it has echoes within it, but in fact the giveaway is the tissue enhancement distal to the mass. So we have a very good idea that this is cystic because of that enhancement. In the compound image in the center of the slide, notice that the enhancement is very difficult to see, and that's because it will have been directed in a different direction in each of the 9 images. So artifacts such as shadowing and enhancement are much less obvious in a compound image because of the change in beam direction between each of the component images that goes to make up the final compound image. Once again in this image, you'll notice that the speckle pattern is much less obvious and less distracting. So to summarize about compound imaging, we get improved display of tissue boundaries and reduced speckle, and many artifacts are reduced. And in general, it's any artifacts which are directed in the direction of the beam. So that includes shadowing, enhancement, edge shadowing, reverberation, and so on. But of course, some of those artifacts can be diagnostically useful, like the enhancement in the previous slide. So sometimes you don't want to lose these artifacts. And the other factor I've talked about already is that the temporal resolution is going to be severely reduced because the machine has to acquire 9 images in order to get a single compound image. For these reasons, compound imaging tends to be used as an optional add-on rather than as a standard mode of imaging. So most users would use standard normal imaging and then switch on compound scanning, sometimes selectively, to reduce speckle, for example. Now we will look at harmonic imaging, which is a completely different modality. Harmonic imaging is possible because there are certain circumstances where the ultrasound pulse can become distorted. Here I'm showing you what can happen when a relatively high amplitude pulse, transmit pulse, is traveling through the tissues. At the points where the pressure is maximum, the tissue is compressed, and this happens to increase the propagation speed of the ultrasound. So the peaks are going to travel slightly more quickly. At the troughs, the places where the pressure is minimum, the tissues are going to be decompressed, and this reduces the propagation speed, and so those troughs are going to travel a little bit more slowly. So over a distance, as the ultrasound is traveling, the peaks will gradually become more advanced and the troughs more delayed relative to the rest of the waveform. So the waveform is no longer going to be a nice sine wave in its shape. It will become asymmetrical, and this has implications relating to harmonics. I'll show you that in a moment. The blue broken line here would be the original transmit pulse, and the red line shows you what's happened after that transmit pulse has travelled by 1 or 2 centimetres into the tissues. So as you can see, the peak is very slightly to the right and the troughs very slightly to the left of where you would expect them to be. This is useful because a distorted transmit pulse is going to give rise to distorted echoes. So if we have a way of producing an image that sees only the distorted echoes, then we know that we will be selectively looking at echoes coming from that core area that I've shaded dark blue. So let me show you what's meant by harmonics. This is a spectral plot. So it's a graph of the range of frequencies present in an undistorted transmit pulse. So this happens to have been drawn for a 6 megahertz pulse. And what you can see is that energy is distributed over a range from about 4 to about 8 megahertz. So we've got a range of frequencies centered on the actual ultrasound frequency of 6 megahertz. So as I said, this is what we would see if we looked at the frequency content of an echo coming from an undistorted transmit pulse. If the transmit pulse was distorted, we will then see what are called harmonics. So we'll see some energy at twice the original frequency, some energy at 3 times, some at 4 times, etc. These are what are referred to as harmonics. The original frequency is called the fundamental frequency, and then the components which are at twice the original are called second harmonics. Those at 3 times the original are called third harmonics, and so on. You'll notice that normally the amplitude of the harmonics drops off, so the second harmonic is significantly lower than the fundamental, the third harmonic is much lower again, and so on. So in practice, we use the information in the second harmonic to identify that this echo has come from a distorted transmit pulse. Now the machine is able to remove information at the fundamental frequency. And so we end up with only the energy from the harmonics. Now the third and higher harmonics are going to become insignificant because those very high frequencies will attenuate extremely quickly in the tissues. The machine is capable of removing the fundamental frequency component from the echoes and retaining this harmonic component. How does the machine actually do this? It's a very clever technique. The machine transmits a transmit pulse, collects all the echoes, digitizes them, and then without moving the beam, it transmits again, but this time the transmit pulse is the exact inverse of the first one. So let's see what this does. I'm showing here just a couple of example echoes from the first transmit pulse and then the second transmit pulse. To the left, I'm showing an undistorted echo. And so what you can see is that the second echo is the exact inverse of the first, because the second transmit pulse was the exact inverse of the first. And because there's no distortion, these are equal and opposite. On the other hand, with the distorted echoes, the second echo is not just the inverse of the first one. If it was, it would be leaning to the left, but in fact it is leaning to the right as well. So these are not simple equal and opposite echoes. Now the way the machine processes this information is to add together the echoes from the first transmit pulse and the second transmit pulse at each depth. The undistorted echoes, as I said, are identical in that they're equal and opposite. They cancel out, and so we don't see them. The distorted echoes, it turns out, the fundamental part of their energy does cancel out, but the harmonic part does not. So we get purely the harmonic. So this is a very clever way of isolating just the harmonics components of the echo signal. Notice, though, that there is a cost. The machine has to transmit and receive twice for each beam position, for each line in the image. So this is going to halve the frame rate. So on the left here, I have an image of a gallbladder, and the arrows are highlighting some artifact echoes likely to be caused by slice thickness within the gallbladder. Here in the center, I have a harmonic image of that same gallbladder. And what you can see is that most of the artifact echoes have now been eliminated. And this is because what I said a couple of slides back about the harmonics coming only from the central part of the beam, this applies when we look across the width of the probe as well in the slice thickness direction. The fact that this image contains only echoes coming from the central part of the beam means that the beam width has been reduced and the slice thickness has been reduced. So you may see that the gallbladder is a little bit crisper and clearer. Here's another example. In the heart, it's very common to have artifact echoes scattered around within the cardiac chambers, and this can be a very significant nuisance because, of course, echocardiographers tend to like to make lots of measurements of dimensions within the heart. In the top left, we have a standard image. In the center, we have a harmonic image. And echocardiographers have found that harmonic imaging improves the clarity of cardiac images so much that they have come to use it as their standard imaging mode. As I said, this will have a lower frame rate than standard imaging, and clearly that's an acceptable price to pay for the clarity that is so significantly improved. I'll be talking in another lecture about contrast agents, so I just want to give you a very brief idea of what ultrasound contrast agents are, because they too have an involvement with harmonic imaging. Here I'm just showing some small micro bubbles of gas, because that's essentially what ultrasound contrast agents are. They work by injecting into the bloodstream tiny gas bubbles just a few microns in size. These then act as very effective scatterers of ultrasound. So the presence of those greatly increases the scattering properties of the blood. The expansion and contraction of the gas bubbles is asymmetrical, and this means the echoes coming back from gas bubbles are distorted. And so that's what I'm showing here in the center of the slide, that we have an undistorted transmit pulse hitting a gas bubble, a distorted echo returns to the probe. So contrast agents are ideally suited for use with harmonic imaging. So this is the idea, that we have a blood vessel with contrast bubbles, and I've shown those as little circles within the bloodstream. I have got scattered echoes coming back from the bloodstream and also the surrounding tissues, and only some of these echoes will be distorted, and I've highlighted those with the green arrows. So it's only the echoes coming from the gas bubbles that are distorted. When we use harmonic imaging, the only echoes we'll see are the echoes coming from the gas bubbles. Harmonic imaging automatically enhances echoes from gas bubbles. Here's a clinical example. Ultrasound contrast agents, being so small, circulate throughout the body and throughout all of the vascular system. Over time, though, the liver removes the gas bubbles from the bloodstream and captures them in readiness for eventual excretion of those bubbles and elimination from the body. So some minutes after ultrasound contrast agents have been injected, they begin to accumulate in the liver. This happens to be very useful because you can then produce images of the bubbles trapped in the liver, and you can look for any regions where this isn't happening, which are likely to be non-functioning liver tissue or some other kind of tissue entirely. Here on the left, I have an image of a liver which has contrast agent in it, but we can't particularly see that. We can't readily appreciate where the contrast agent is. Here on the center of the slide, I have a harmonic image. It happens to have been color-coded rather than being just a grayscale image, but that's neither here nor there. And what we can see is that there are some voids, some areas where the contrast bubbles have not been taken up by the liver. So that's either non-functional liver tissue or some other kind of tissues entirely. This has become a very useful method of looking at liver function. Here's another example of the same thing. And once again, in the grayscale image, it's not possible to see the contrast agent at all, but in the harmonic image, which is the color-coded one, the harmonic imaging highlights the presence of the contrast agent, and therefore it's very easy to see which parts of the liver have taken up the contrast bubbles. Let me summarize about harmonic imaging. It effectively reduces the beam width and therefore improves lateral resolution. Note, by the way, that it doesn't improve axial resolution. It reduces slice thickness, as I explained a few minutes ago, and this is going to help to improve contrast resolution. Harmonic imaging also reduces some other artifacts, in particular side lobe artifacts. Note, by the way, that it doesn't affect the speckle pattern significantly. And then, of course, we've seen that harmonic imaging greatly enhances echoes from ultrasound contrast agents. So these are all useful properties. And of course, as usual, there's a but. The harmonic imaging automatically reduces the frame rate by a factor of 2. It also reduces penetration because, of course, we're now looking at echoes coming back at twice the transmit frequency. And they will, of course, be attenuated more quickly than the fundamental frequency. So overall, what we've seen is that compound imaging is a nice add-on feature which can be turned on and off at will. It reduces speckles significantly and greatly improves tissue boundaries, but it very significantly degrades temporal resolution. Harmonics reduces artifacts, improves resolution, and enhances contrast bubble echoes, but it too slows down the frame rate and reduces penetration.